All right, welcome back. So this is another ALEKS topic called Deducing a Rate Law from Initial Rate Data. This is a great topic. It's definitely a little confusing though, so we're going to go ahead and do two different examples of this topic. We'll see how timing goes, so either it will be after this video or I will link to another video with another example of this problem. So in this problem, the sort of key thing, the thing that we need to sort of keep in mind is what the question is asking. And this type of rate equation or rate law, this is really the key aspect. And we need to understand what's going on with this before we really do the problem, because if we don't, then it doesn't really make sense what we're doing. So this rate law is going to tell us what the reaction rate is, the initial rate of reaction, that's this rate here. And that's going to equal some constant K that's specific to that chemical reaction times the concentration of the reactants raised to some power X or Y. So these are my reactants, N2 and H2. So this would be some reaction where I'm reacting nitrogen with hydrogen, maybe to form ammonia. And the rate of that reaction is going to be determined by the order of these X and Y. So we call these the order in X, the order in N2, and the order in H2. And if you add those together, that's the overall order of the reaction. So not specifically important for this problem, but that's sort of what we're looking for in a problem like this. We're trying to solve for this value X and trying to solve for this value Y using this information over here. So now let's orient ourselves to this information over here. What this is sort of saying is we're going to essentially do three different experiments. Experiment 1, we're going to start with an initial concentration of N2 of 0.48 molar, an initial concentration of H2 of 1.11 molar, and when you mix those two things together, this is the initial rate of the reaction. This is how fast the reaction is going to go. If we look at experiment 1 to experiment 2, in experiment 2, I'm going to increase the concentration of N2. I'm going to put more N2 into my reaction mixture, so going from 0.48 molar to 1.4 molar, but I'm going to keep the concentration of H2 the same. So when I do this, when I make this change, whatever change I observe in my initial rate of the reaction, that's going to be due to this change in N2. Since this H2 stays the same, as I increase the concentration of N2, then any increase I observe over here is due to that increase in N2. That's going to tell us what this X value is. So the way that we'd actually do that, the way that we'd sort of solve for X, I'm going to compare experiment 2 over experiment 1. And I'm choosing to put experiment 2 on the top because 1.4 is a bigger number than 0.48. It's going to make my numbers make a little bit more sense. So as you're doing this comparison, 1, you need to figure out which two experiments have only one thing changing. So the H2 stays the same here between experiments 1 and experiments 2, but my N2 concentration is changing. So any change I see over here, I can correlate that to that change in N2. So I'm going to figure out for experiment 1, or excuse me, for experiment 2, I started with 1.4 molar, 0.48 molar for experiment 1, and that equals 2.92. So what this is telling me, what this information here is telling me is that I've increased the concentration by 2.92 times. Typically, if we're doing these experiments by ourselves, we'll do like a nice doubling or a nice tripling. But in this ALEKS topic, it wants us to sort of look at some numbers that aren't exactly the easiest numbers to deal with. But suffice it to say, going from experiment 1 to experiment 2, I've increased my concentration of N2 by 2.92 times. So then what we're going to do is we're going to say, well, what happens to the rate of the reaction? The rate of the reaction goes from 0.56 molar per second and 0.191 molar per second. So that ratio equals 2.93. So these two numbers are essentially the same, right? If you look at this number 2.92, 2.93, what that's telling us is that for every time we increase the concentration of N2 by a factor of 2.92, we see the same increase in our rate. So this, these are our rates, so 2.93, that would be sort of this increase in the rate. The increase in the rate is the same as the increase in my concentration. That tells us that the X value is 1. And the sort of way that you might write that out to sort of calculate it, I'm going to take my rate, 2.93 equals, So the K and the H2 concentration, that's going to be constant. Remember, our H2 concentration between these is constant between experiments 1 and experiments 2. And so this all right here would be constant. Our K value is obviously going to be a constant. So we can actually relate our change in our N2, which is 2.92, to our change in our rate. So basically we're solving this equation for x, and since we can see that these are essentially the same number, that tells us that x equals 1. So we figured out our order in N2. Let's do the same thing for solving for y. So solve for y. So for y, that's our order in H2. I'm going to be looking for 2 experiments where the only thing that changes is the concentration of H2. So experiment 1 and experiment 3, I've got a change in my H2 concentration from 1.11 molar to 4.27 molar, and my N2 concentration stays the same. So because my N2 concentration stays the same between experiments 1 and experiments 3, that's a good sort of comparison to make. So I'm going to take experiment 3 on the top and experiment 1 on the bottom, because again, I want to put the larger numbers on the top. It just gives, it makes these numbers make a little bit more sense. It's easier to deal with, I guess. So if I do that, then I'm going to say 4.27 molar on the top over 1.11 molar on the bottom. So experiment 3, experiment 1, and then this equals 3.85. So going from experiment 1 to experiment 3, we're going to increase our concentration of H2 by 3.85 times. And then we want to see what happens to our rate. So when I do that, 2.83 molarity per second over 0.191 molarity per second. So this ratio, when I go from experiment 1 right here to experiment 3 right here, this change in rate, it goes from 0.191 to 2.83. Well, how much is it changing in rate? So that, if you do that calculation, you get a value of 14.8. So this is, now we've got a difference in numbers. So now we're going to do a similar thing that we did here to figure out what that order in H2 is. So I would say my rate increases by a factor of 14.8 when my H2 concentration increased by a factor of 3.85. I'm going to solve this for y. And if you solve this for y, there's a number of ways, like mathematically we could solve it somehow. But what I would do, it's going to either be 1, 2, or 3 realistically. So I would just sort of plug in, well, what's 3.85 squared? It's exactly 14.8. So, figuring out, okay, looking at this, how do I solve for y? I would just do guess and check personally. It's most likely going to be 1 or 2. Might be 3, but we can sort of, judge. But I would just test it out, see what would happen. 3.85 to the second power gives you exactly 14.8. So we know that the order in H2 is 2. So what does this mean? Basically what this means is that when you change the concentration of H2, the rate is going to change by a bigger factor, right? It's going to, instead of when I when I multiply this by 3.85, when I increase my H2 concentration by 3.85%, not percent, by 3.85 times, there we go, my rate is going to increase by 14.8 times. That's what we've figured out by doing our comparisons up here. So this should make sense, hopefully. If it doesn't, definitely let me know, and I can try to fix that explanation up a little bit. But the take-home message is, we want to compare experiments where only one thing changes, and then we're going to relate that one change. So between experiments 1 and experiments 3, the only thing that's changing in terms of our concentrations is my H2 concentration. So this change in my H2 concentration from 1.11 to 4.27, that's what's causing this change in my initial rate of the reaction. So we want to choose those experiments carefully. So now we've got the answer for this part here. The rate equals, I'm just gonna write the whole thing, K times the concentration of N2, and that's to the first power. So we can just leave it like that, times the concentration of H2 to the second power. And then for our K value, we can really choose any of these experiments to sort of plug in to solve for our actual K value. So what I mean there is I'm just going to choose experiment 1, and you don't have to choose experiment 1. You can choose any experiment you want. And I'm going to plug in the values. So 0.191, that's my initial rate of reaction. My concentration of N2 is 0.48. My concentration raised to the first power. Concentration of H2 is 1.11, raised to the second power. And I'm going to solve for K, right? So just solve this for K. You should end up for this problem with the value of 0.32. Now the units, so the units are very important. So these units on K, they're going to be variable. They're going to change based on what my order of reaction is, basically. And they need to be whatever units that are going to be on K need to work out essentially so that our units for our rate are molarity over seconds. So we know that this, so if we write out rate equals, we'll just do it up here actually. That'll save us some time. So we know that the units on the rate are molarity per second. We need to figure out what our units on K are. We know what our units on N2 and H2 are. That's molarity to the first power times molarity to the second power, right? So this stands for molarity. So basically in here, I need to figure out, well, what do my units need to be so that, it cancels out and I get the proper units over here. So it's always going to be 1 over molarity such that it cancels out. 2 of them leaves 1 of them times seconds. So 1 over molarity squared times seconds. That set of units will allow us to end up with these units, the proper units for our rate. So the way that we're gonna calculate that or show that, I guess, we can get rid of that, would be molarity to the -2 times seconds to the -1. So that's the easiest way to enter that on ALEKS. So when I actually, enter my answer here, 0.32, 2 sig figs, because I've got 2 sig figs in my value here, molarity to the -2, and then you need to use this little symbol to put a dot, seconds to the -1. So that would be the proper units for this problem. So again, these units are going to vary based off of whatever our orders are. So if our order was 2 and 2, that would change it to molarity to the -3 times seconds to the -1. It's always going to be something like this, but we need to make sure we know what's going on with this molarity here. But we, if we do a treatment like this, we should be able to figure out, well, what do I need to have there to make it so that my units on the rate sort of work out and get me where I want to go. Okay, so I will do another example in another video, maybe not right away, but I'll do another example in a little bit to go over just one more example for how to solve this problem. But hopefully that makes sense. Hopefully that works for you. If not, just let me know, and we'll keep going. All right.